This is the intro to Moment of Inertia, and in this video I just wanted to kind of walk us through how to determine, how to mathematically determine the resistance that a given object will have to rotating about a given axis. And also we'll determine the resistance that that object would have rotating around a polar coordinate. So utilizing this, we should be able to determine what an appropriate beam design was, or is something going to be stable, and then later on in other classes we'll be able to determine how much deflection will occur, and just all these various things. So it's very foundational knowledge that you'll get here, and we'll just sum it up with a quick example. Basically, any rotation that will occur, you can assume that it will go around an x and y axes. You can just true up the x and y axes to that axis of rotation, right? And I drew a little picture here that has, first of all, a dA, which is just a given area, and you have these two axes, x and y. Now, if that box, that small box, dA, was to go around, say, the x-axis, it would be resistant in the sense of around x-axis would be the integral of y squared dA. Now, dA is not any specific size. It's just, I mean, we don't have a specific shape here, but it could be any size. At this point, it's really, really tiny. And let me just go on with the y-axis. You'll have the integral of x squared dA, and then rather than determining what, well, okay, the polar rotation or polar resistance around point O, so for that box to rotate around this point O, the origin of our axes, it would be the integral of r squared dA. And remember that r squared equals x squared plus y squared. So just remember that from in geometry, right? So your r is going to be something like in the middle. Okay, so one more observation that I want us to make is that the rotation around this origin is going to equal I x, the inertia around about x-axis, plus the inertia about the y-axis. So we can actually almost ignore trying to find the polar. We could just find the other two and then add them up. So that kind of simplifies things for us. And rather than going through all the details on how to derive this, let's just go right into an example, and I'll show you how to use it. And that way, we might gather a better understanding of what's going on here. So first of all, let's just draw something simple that we know. Let's just draw a quick box, okay? So you have this box, which has, let's say this is our y, and this is our x. If we have a height h and a base b, then, and here's O, what is, first of all, what is the inertia about x, the inertia about y, and j? Well, I mean, we just use the equations above, and then we can kind of work it out. Now, this is just a general form, but I just wanted us to know how to determine this, right? Well, first of all, one thing that I want us to find out is, what is dA going to equal? Well, dA, since this is a box, in terms of y, it would be, well, the area of a box is base times height. So we know that. So what would dA be? Well, If it's dependent on y, then it would be base times dy. Or if it's dependent on x, then dA would equal height times dx. And all that's saying is, what direction are you coming from? Are you coming from this way, going right? So is x the one that's changing, or is it y the one that's changing? So which direction are you going? And that's just that'll all take effect in the various ones. Let's walk right into it. Ix equals the integral of y squared dA, which we know equals y squared b dy. Why did I pick that one? Well, simple. There's a y here, and we have y already in our equation, so just work it that way. If you toss the b out, because that's not going to make a difference, you have y squared dy, which when you solve for that between h and 0, you will get b 1/3 y cubed between h and 0, which means 1/3 bh cubed, which is great. So we know that when this is rotating about the x-axis, we will have 1/3 base times height cubed. Okay, well that's just about the x-axis. This is Ix. What about Iy? Iy is going to go through something very similar. The equation for Iy is x squared dA, which is x squared h dx. So thus, when we work that out, we get h integral of x squared dx, which goes to 1/3 h x cubed between b and 0, which goes to 1/3 h b cubed. Notice that these are similar but different. And what makes them different? Well, it seems that the further away from that axis, in the case of y, the further away, b is the highest, it seems to be the higher affecting term here because it's cubed. It's the further away an object gets from the axis of rotation that you gain more resistance. And what would the j be? Well, the j, we can just kind of do a linear combination of them. Ix plus Iy, which I'll just say it's going to be 1/3 bh cubed plus 1/3 hb cubed. And we could just leave it at that. We don't need to. You can simplify it more, but there's no real point. You have the solution. It's obviously it can simplify out more though. So don't worry. You won't need to do this for every single shape. Every single shape is pretty much tabulated in a majority of your books. But I just wanted you to know that this is the type of process that they go for each and every point of rotation. So someone had some kind of software or way too much time, and they went through all these little points to find where convenient points are to tabulate them, so that you can always refer back to that, and you just plug and chug at that point, and you'll be able to use them 90% of the time. One thing that I want us to realize is that area is analogous. I don't know what the sign for analogous is. I don't know, proportionate maybe. I don't know, to mass though. And that's all I'm saying is that basically area and mass, you should consider them the same thing when we're determining inertia, because you can completely just one for one switch mass with area. And it's actually more appropriate for area to be our primary unit, for mass to be our primary unit, because that's, if you had different material types, that would influence, the heavier material would influence per square inch or whatnot, rather than the lighter material. So let's just go through some of the tabulated tables, and then we can start off with some examples.